Hello everybody, I will present for you now our work called Schema-agnostic blocking for streaming data. This work is the number 1661 from the track Database and Big Data Management. Our work was developed with a consortium between UFCG, Federal University of Campina Grande from Brazil, and Tampere University from Finland. The idea of our work is handled with intensive data tasks. Intensive data tasks commonly handle a lot of data and with complex algorithms. In this sense, we also have the entity resolution task. The entity resolution task is the task that tries to find similar records between two data sources, two or more data sources. The idea here is try to discover which record represent the same entity in the real world. Moreover, we can also handle with heterogeneous data. Heterogeneous data is the data that can be stored in different formats, but that don't follow the same schema. For example, XML or JSONs. This kind of data don't follow a hard schema, and the records can follow different schemas with different attributes. Moreover, here we handle streaming data. Streaming data is the kind of data that's continually sent for the data source. For instance, Twitter. We also handle big data because we consider that this streaming data will send, as I told you, for example, Twitter that send a lot of tweets, a lot of data in each second, in each minute. In this sense, we can explain better the entity resolution tasks. For instance, you have the entities. You have three entities. Two entities represent Alan Turing, the other Albert Einstein. Using the entity resolution task, you will find the match or the correspondence that represent the same entity in the real world, in our case, Alan Turing. But the main problem of entity resolution task is because the computational cost is a quadratic one. And it occurs because you need to compare all entities against all entities of the other data source. In this sense, we have a quadratic cost. Okay, when you handle with heterogeneous data, we need to try to don't have 100% certain about the schema, because they don't follow the entities don't follow the same schema. In this case, we don't trust in this schema, and you can use the data, or in other words, you can use the attribute values to perform that resolution. In that way, we also have another challenge involving the streaming data. As I told you, the main problem here is because the data is continuously sent, and the data source receives continuously this data, and of course the main question is because the behavior of this data is increase the number of entities in the data source. Okay, but when you're talking about entity resolution, we also can have a kind of step before the entity resolution. Is called blocking. The idea of blocking is try to construct clusters based on the similarity of the entities, and just compare the entities that stay in the same blocks. The idea here is trying to avoid the quadratic cost of the entity resolution task. Then we can, based on some similarity between the entities, construct this block. Since we are handled with heterogeneous data, we can trust in the schema. In that case, we use the data of the attribute values. In this data, we can split them in tokens. For instance, each part of the attribute value we consider it as a token, and all the entities that share the same token will be put in the same block. Look that. We can have, for example, Alan, the token Alan, the token Turing, the token Professor, the token Mayor. Since Alan Turing, these two entities, Alan Turing, share Alan and Turing, they will put in the same block the block represented by Alan and represented by Turing. But the main problem here is because we can, if you put these blocks to be compared, the entities of these blocks to be compared in the entity resolution task, we have unnecessary comparison because we will compare these two entities here in the cluster in the block Alan and also here in the block Turing. To avoid it, the meta blocking technique was created, and the idea of the meta blocking proposed by is considered a state of art. The idea of meta blocking is generate a graph, a similarity graph, and the similarity value between the entities, for instance here 2, is based on the co-occurrences in the blocks. For instance, the number 2 is represented by these two blocks that these two entities are that's two entities co-occurs. Okay, since we have these three entities that share the token Professor, we have the similarity 1 for between these three entities. Okay, but considering that we have these entities, we also the idea of metablock is prune these entities and prune based on the similarity value. The idea here is just maintain the high values, the high similarity values. And for instance, you can for instance remove some edges and just maintain, for instance, these two entities and to be compared in the entity resolution task. Okay, in that sense, we can also we develop the parallel-based incremental blocking. Is our approach called PI block. The PI block is a novel schema-agnostic blocking technique since it handle with heterogeneous data, and they use Spark, the framework Spark, to propose a efficient parallel workflow. Moreover, we also handle streaming data and using incremental processing to handle with this stream data. Since the stream data increase continuously, the idea here is also we use a time window to discard old entities. This information will be to be explained better in the next slides. And also we provide strategies to avoid unnecessary entity comparisons during the block construction. Okay, the first the workflow of the PI blocks is split in two jobs, Spark jobs. And the idea here is, okay, we have inputs, we have entities provided by data source 1 and data source 2, and using the token extraction, we have the blocks based on the tokens. For example, here you have the token A, the token B, the token C, and all the entities that share the same tokens. Okay, in that case, we have the block generations, because based on the token extraction, we can have the blocks to be generated, and all the entities that share the same block we put in the same block. That share the same token we put in the same block, and okay, we have the first job, generate the blocks based on the token extraction. After that, we use the pruning, and that pruning, the idea here is just to maintain that blocks that is just to maintain the entities that have the high similarity values. For instance, based on the co-occurrence of that blocks here in the block generation, we can prune and just maintain the entities with high values, and after that very high values, we just maintain that. After the pruning, we have the outputs with the entities that need to be compared in the next steps. In the second job, we execute the pruning step. Sorry. Okay, but we need to consider that you just have only one increment. Here we have another increment. In that new increment, we received more 3 entities here. These 3 entities, we also have a token block extraction. We have the blocks that need to be considered here. But the main question is, okay, we need to also consider that the block generation that we generate in the increment 1. In that case, for instance, we can avoid some unnecessary comparisons, because you can mark, since entity 1 and entity 4 was compared in the first increment, we don't need to compare again, and that's why we have marks here to try to avoid that entity 1 and entity 4 needs to be compared again. In this case, we just need to compare entity 1 with entity 5, entity 1 with entity 7, entity 4 with entity 5, entity 4 with entity 7. In that case, we avoid to have other necessary comparisons also related to the blocks, because here you just compare block 1, the entities involved with block 1, block 6, block 7, and block 8, because the other blocks not have changed or updated. In that case, we don't need to consider that entities. Okay, after the block generation, we need to have the entity values, the similarity between the entities, and after generate the pruning, we can have also the information here about the entities that the similarity value, the entity pairs, or the entity pairs with high similarity that need to be compared in the entity resolution task. Okay, this workflow is the PI block workflow that you have considered also the incremental behavior, and consider that the inputs will be sent in each increment. Okay, but you have a big problem regarding the incremental data and also related to streaming data called memory consumption. This memory consumption, the main problem is because the data is continually sending, and if you consider all the entities sent to our approach, we don't have memory enough to handle with a lot of this data. And the idea here is have a kind of block window, a time window. That time window we considered the entities that we still that stay in old entities need to be discarded. For instance, we have a first window here, and that window in purple we'll consider that entities, but of course we have a past, and that's why, because you have this other window in red, and that window in red we consider that entities. For instance, entity 1, entity 3, entity 2, entity 4, we consider that entities. But when you have slide this window for time 3, you can have this window in blue. In that window in blue, we not just considered entity 2, entity 4, entity 5, entity 7, and entity 1 and entity 3 was discarded because not present in this window. And the idea here is trying to discard the old entities, because you can't consider all the entities because the data is continually set. This is the idea of the time window. Okay, now we need to analyze the related work and analyze all the state-of-art approaches. And you can consider the meta blocking. Okay, the meta blocking is a schema-agnostic approach, and also we propose in parallel, but they don't consider the incremental behavior, and also does not handle with streaming data. About iGraph, the iGraph is an approach that it's not schema agnostic, because they use the relational database and they use the schema to guide it. But it's proposed in parallel and also consider the incremental behavior. But they did not consider the streaming data. Other approach is Strider, and the Strider also is proposed but for a relational data source. That's why it's not schema agnostic, but it's in parallel and handle stream. But just the PI block handle all this idea. That's why the PI block is a novel blocking technique, because they consider the schema agnostic, proposing parallel and incremental behavior, and also handle with streaming data. It's the first, at least in the best of all knowledge, it's the first idea, the first strategies that handle all these four challenges. When you experiment the PI block, we need to try to have a state of art. Since the meta block is the more similar approach, the most similar technique, we propose the streaming meta blocking. The streaming meta block, we adapt the meta blocking to receive streaming in an incremental way. And we propose that these two ideas, it's a kind of baseline, the streaming meta blocking and also the PI block. Okay, about the quality metrics, we have pair completeness. It's a kind of recall. Pair quality, it's a measure. It's really similar with precision, but for blocking techniques, and also reduction ratio. It's a metric trying to analyze how the number of comparisons that we can skip using the blocking techniques. About efficiency, we use the execution time, and also we measure the memory consumption. We use for a real world data source that we can have now some information about our data source. We can check also in the paper. But when you check the quality evaluation, when we use the window, of course we can have a decreasing of the pair completeness, because you are using a window and discard some entities. But also, since we discard some entities, we also increase the pair completeness or the pair quality and the reduction ratio. And of course, as we increase the size of the window until they use, for example, here use all the blocks, or you consider all the entities, you never discard. In that case, we don't use in the window. You can have an increasing number for pair completeness, but you have a small decreasing for pair quality and reduction ratio. About the memory consumption, notice that using window, we have a decrease in the memory consumption. The same occurs for the BLP and RCM database, and also IMDb versus DBP is the biggest one data source. And okay, about the execution time, you have also the same standard, because the PI block with window, we have a better result about the execution time for all the four pairs for data source. For instance, also, since we are using a different workflow that we discussed some slides before, the PR block also have better results regarding the meta blocking, the meta blocking technique. In that case, we also have, for example, IMDb versus DBpedia. You just have results for a PI block because they use the window. They use window, because in the other case we have a blast of memory. You can execute using the PR block without window or the meta blocking one. Then, concluding my presentation, the idea here is that the PI block, it's an incremental schema-agnostic blocking technique that also overcomes the state of art, the streaming meta blocking, because they use a efficient parallel approach handled with streaming data. The next steps for future works, you need to improve the efficiency of PI blocking to handle high memory consumption. For instance, for big data, as I told you, we have some problems about that for IMDb versus DBpedia, and also perform some experiments for considering large data source. Okay, of course I'm open. You can send me some questions, and really thanks to present my work here.